Welcome! In this session, we'll dive into an exciting problem, increasing-decreasing string. We'll explore the problem requirements, walk through intuitive approaches, and break down the solution step by step. Stick around to sharpen your algorithm skills. In this problem, we are given a string S that consists of only lowercase English letters. The goal is to sort this string using a specific pattern. First, we pick the smallest character from the string and append it to the result. Then, we continue picking the smallest character that is greater than the last appended character, repeating this process as long as possible. Once no more characters can be picked in increasing order, we switch to picking the largest character from the string and append it. From there, we continue by picking the largest character that is smaller than the last appended, again repeating until no more characters can be picked in decreasing order. This alternating process between ascending and descending selections continues until all characters in the string are used up, and the final result is returned as the sorted string. The input is a string of lowercase letters, and the output is the resulting string after applying this method. Let's look at some examples to understand the process better. In the first example, the input string is S equals A abbuk. The output is abkba. Here's how this result is achieved. In the first iteration, we start by picking the smallest characters in ascending order, which are A, B, and C. Then, we reverse the process and pick the largest characters in descending order, which are C, B, and A. This completes one full cycle. We repeat the same process for the remaining characters in the string until all of them are used up, and the final output is formed. In the second example, we have the input S equals rat. The output here is art. The process begins by selecting the smallest characters in ascending order. We pick A, then R, and finally T. Since all characters in the string are used in this single cycle, the process ends, and art is the resulting output. Similarly, in the third example, the input string is S equals LeetCode. The output is T. To achieve this, we start with the smallest characters, selecting C, D, E, L, O, and T in ascending order during the first cycle. After picking the smallest characters in the first cycle of the example S equals LeetCode, we then switch to selecting the largest characters in descending order. Here, we pick E. The process alternates between ascending and descending selections until all the characters are consumed, resulting in the output T. Moving on to the constraints, the string S will have a length between 1 and 500 and will only consist of lowercase English letters. There are also some edge cases to consider. For example, if the string contains only a single character, such as S equals A, the output is simply A. If all characters are the same, such as S equals CCCC, the output remains CCCC. In cases where the characters are in random order with duplicates, such as S equals kabak, the given sorting method ensures that the characters are processed in the specified alternating pattern to produce the correct result. To solve the increasing-decreasing string problem, one straightforward approach we can consider is the brute force method. The intuition here is simple. We repeatedly scan the string to find the smallest character, append it to our result, and then remove it from the string. After that, we reverse the process by scanning for the largest character and append it as well. This alternation between smallest and largest continues until no characters remain in the string. The process starts with an empty result string, and while the input string isn't empty, we alternate between selecting the smallest and largest characters in sorted order. This method directly adheres to the problem's requirements by following a scan and remove strategy each step of the way. However, the brute force approach, while conceptually simple, is computationally expensive. Each scan involves traversing the entire string, and removing characters repeatedly adds to the overhead. This results in a time complexity of n squared, where n is the length of the string, making it inefficient for larger inputs. The trade-off here is clear. Although this approach is easy to understand and implement, its inefficiency makes it unsuitable for competitive programming or scenarios where performance is critical. To address these limitations, an optimized approach using a frequency count can be employed. By leveraging the fixed range of lowercase letters, we can track character frequencies in a small array, allowing us to efficiently select the smallest or largest characters without needing to scan the string repeatedly. This removes the need for sorting or repeated traversals altogether. In the optimized approach, we start by building a frequency array of size 26 to count the occurrences of each character in the input string. This array essentially acts as a histogram, where each index corresponds to a letter from A to Z. Once the frequency array is prepared, we initialize an empty result string and alternate between traversing this array in ascending and descending order. During each traversal, we append characters to the result while decrementing their frequency in the array. This ensures that we process characters in the required order, smallest to largest, then largest to smallest, until all characters are used. The efficiency of this approach lies in its simplicity. With a single iteration to build the frequency array and a constant time lookup for each character, the time complexity of the entire process is O(n). Additionally, the fixed size of the frequency array means the space complexity is O(1), making this approach both time and space efficient. The frequency count approach is the strategy of choice for this problem due to its efficiency and simplicity. Unlike the brute force method, which involves repeated scans and removals, the frequency array allows us to directly access character counts and append them in the desired order. This drastically reduces the time complexity from O(n)² to O(n), which is especially important for handling larger inputs. A key insight here is that the problem can be reduced to sorting characters in alternating directions, a task that the frequency array handles effortlessly. Additionally, by leveraging the fixed range of lowercase letters, we simplify the process and avoid traditional sorting altogether. While the brute force method might seem easier to code initially, its inefficiency makes it impractical, especially as the input size grows. The frequency count approach strikes the right balance between performance and clarity, making it the optimal solution. In conclusion, the optimized approach using a frequency count not only adheres to the problem's constraints but also ensures computational efficiency. By reducing the time complexity to O(n) and requiring minimal space, this method handles the problem elegantly while maintaining clarity in implementation. It avoids unnecessary computations and directly leverages the fixed range of characters, making it well-suited for both competitive programming and real-world scenarios. Ultimately, this approach combines the best of both worlds, simplicity in concept and efficiency in execution, providing a robust solution to the increasing-decreasing string problem. The problem asks us to rearrange the characters of a given string by alternately picking the smallest and largest remaining valid characters until the entire string is processed. To solve this, we start by parsing the input and setting up the necessary data structures. First, we convert the input string into a list of characters, ensuring it's easy to manipulate. Then, we sort this list lexicographically so that the smallest characters come first and the largest come last. We initialize two pointers, one called left, pointing to the start of the sorted list, and another called right, pointing to the end. These pointers will help us efficiently track the smallest and largest unprocessed characters. Finally, we create an empty list called result, which will store the rearranged characters in the correct order as we process the input string. Once the setup is complete, the main logic revolves around alternately selecting the smallest and largest characters. This is achieved using a loop. In each iteration, we first append the smallest unprocessed character, located at the left pointer, to the result list. To prevent reusing the same character, we increment the left pointer. Next, we append the largest unprocessed character, located at the right pointer, to the result list, provided it still exists. Similarly, we decrement the right pointer to exclude this character from future iterations. We repeat these steps until all characters have been processed, which happens when left surpasses right. After the loop, the result list contains the characters in the desired order. We then join the elements of this list into a single string and return it as the output. This approach uses a sorted input list, two pointers for efficient tracking, and a dynamically updated result list to ensure optimal performance both in terms of time and space. The algorithm is built on a few key insights. By sorting the input, we ensure that the smallest and largest characters are readily accessible via the left and right pointers. Using a two-pointer technique minimizes unnecessary scans of the input list, making the process efficient. Handling edge cases is straightforward. For instance, if the input contains a single character, the output is the same as the input. If the input is already in alternating order, the algorithm naturally handles it through the selection process. When all characters are identical, the output remains unchanged as well. In terms of complexity, the sorting step requires O, n log n, time, while the alternating selection loop runs in O, n. This results in an overall time complexity of O, n log n. Space complexity is O, n, due to the input and result lists. For very large inputs, in-place modifications of the list could further optimize memory usage, making the algorithm both practical and efficient. Let's walk through an example with the input string ECBA. First, we sort the string, resulting in the list A, B, C, D, E. We initialize left at 0, right at 4, and result as an empty list. In the first iteration, we append the smallest character at left, which is A, to result, making it A. We then increment left to 1. Next, we append the largest character at right, which is E, to result, making it A, E, and decrement right to 3. In the second iteration, we append the next smallest character, B, and increment left to 2. Then, we append the next largest character, D, and decrement right to 2. At this point, result becomes A, E, B, D. In the final iteration, left and right both point to the middle of the list, where the character C is located. We append C to result, making it A, E, B, D, C. After this, left increments to 3 and right decrements to 2, causing the loop to exit since left is now greater than right. The final result list is joined to produce the output string EBC. This demonstrates how the algorithm systematically rearranges the string by alternately selecting the smallest and largest characters, ensuring correctness and efficiency throughout the process. This solution begins by counting the frequency of each character in the input string S. This is done using a list char underscore count of size 26, where each index corresponds to a letter from A to Z. The frequency of each character is incremented in this list based on its ASCII value, calculated using ord, char, ord, A. Next, we initialize an empty list called result, which will hold the characters in the desired order. The algorithm then enters a loop that continues until the result list contains all the characters of the input string. The first part of the loop appends characters in increasing order, from A to Z. For each index I in the range 0 to 25, if the frequency of the corresponding character, based on char underscore count, I, is greater than 0, the character is added to result, and its count in char underscore count is decremented by 1. The second part of the loop appends characters in decreasing order, from Z to O. This is done using a reverse traversal of the char underscore count list, iterating from index 25 to 0. Similar to the first part, characters are added to result only if their frequency is greater than 0. Finally, after the loop completes, the result list is joined into a single string using .join, result, and returned as the output. This ensures that the final result string is constructed according to the problem's requirements. The algorithm efficiently handles the construction of the string by leveraging the frequency array and iterating over it in both increasing and decreasing order. The time complexity is O, n plus k, where n is the length of the input string and k is the constant size of the alphabet, 26. This makes the solution highly efficient for the given constraints. Here, we begin the Java implementation for the problem. First, we import the necessary packages and define our solution class. Inside the sortString method, the first step is to count the frequency of each character in the input string. We initialize an integer array, charCount, of size 26 to represent the 26 lowercase English letters. By iterating through each character in the string, we increment the count at the corresponding index in the array. For example, if the character is A, we increment charCount 0, and if it's B, we increment charCount 1, and so on. Next, we create a string builder object to construct our result and store the length of the input string in the variable n. Now, we proceed with a while loop that continues until the length of the resulting string matches the length of the input. Inside this loop, we first append characters in increasing alphabetical order. We do this by iterating from index 0 to 25 in the charCount array. If the frequency at a given index is greater than 0, we append the corresponding character to the result and decrease its frequency. This ensures that each character is processed in ascending order before moving to the next step. After processing characters in increasing order, the next step is to handle them in decreasing alphabetical order. For this, we iterate from index 25 down to 0 in the charCount array. If the frequency at a given index is greater than 0, we append the corresponding character to the result and decrement its frequency. These alternating loops, one for increasing order and the other for decreasing order, continue until the result string reaches the same length as the input. Finally, once the while loop completes, we convert the string builder object to a string and return it as the output. This ensures that the characters are appended in the desired zigzag pattern, alternating between increasing and decreasing order, as required by the problem statement. To solve this problem, we start with the example input s equals a abbook. The first step is to count the frequency of each character in the string. We create a list, char_count, with 26 zeros, each representing a letter from A to Z. Then, for every character in the string, we increment its corresponding count in this list. After processing the input, the char_count array becomes 4, 4, 4, 0, 0, 0, indicating there are 4 A's, 4 B's, and 4 C's, while all other letters have a count of 0. Next, we append characters to our result in increasing order. This involves iterating over the indices from 0 to 25, checking if the count at each index is greater than 0. If it is, we append the corresponding character to the result and decrement its count. After one pass in increasing order, the result contains a, B, C, and the char_count is updated to 3, 3, 3, 0, 0, 0. Following this, we append characters in decreasing order by iterating backwards from index 25 to 0. Using the same process, characters are appended again, resulting in a, B, C, C, B, A, and the counts are further reduced to 2, 2, 2, 0, 0, 0. To complete the solution, we repeat the process of appending characters in both increasing and decreasing order until all characters are used. For this example, we continue alternating these passes until the result contains all occurrences of A, B, and C. The final result list becomes A, B, C, C, B, A, B, C, C, B, A. Joining these characters together gives the output string apba. Now, let's look at a second example where the input is s equals rat. Here, we first compute the char_count, which results in 0, 0, 1, 0, 1, 1, 0, 0. This indicates that R, A, and T each appear once. During the increasing order pass, we append A, then R, and finally T to the result, leaving us with A, R, T, and an updated char_count with all zeros since all characters are used. In the decreasing pass, no characters remain to append, so the result remains unchanged. The final string for this example is simply art. In the third example, the input is s equals LeetCode. Here, we calculate the char_count as 1, 0, 3, 1, 3, 0, meaning L appears once, E 3 times, T once, C once, O once, and the rest have a count of 0. For the first increasing pass, we append C, E, L, O, and T to the result. This leaves us with the intermediate result equals C, E, L, O, T, and the char_count updates to 0, 0, 2, 0, 2, 0. During the decreasing pass, we append T, O, L, E, and C in reverse order, giving C, E, L, O, T, T, O, L, E, C. We continue alternating between these two passes until all characters are used. The final result becomes sella-to-leak, which is the desired output. This algorithm ensures we alternate between increasing and decreasing orders while efficiently building the result based on character counts. By avoiding repeated sorting of the input, the solution is both simple and efficient. To understand the time complexity of this solution, let's break it down step by step. First, we count the frequencies of all the characters in the input string. This involves initializing a list of size 26 to keep track of the counts for each lowercase letter, and then iterating over the string once to update these counts. This operation is linear in relation to the length of the string, so it takes O(n) time. Next, we move to the process of building the result string. Here, the algorithm uses a loop that continues until the result string reaches the same length as the input. Since at least one character is appended to the result in each iteration, the loop runs at most O(n) times. Within each iteration, there are two for loops, one that processes characters in increasing order and another in decreasing order. Each of these loops scans through the 26 possible characters, which is constant work, or O(1), per iteration. Multiplying this O(1) work by the O(n) iterations of the loop, we find that building the result also takes linear time, or O(n). Once the result list is fully built, the final step is to convert it into a string using the join operation. This operation involves traversing the list of characters to produce the final string, which takes n time, where n is the length of the string. Combining the time complexities of all these steps, we have n for counting frequencies, n for building the result string, and n for joining the list. Adding these together, the total time complexity of the solution is n. Now, turning to space complexity, the char_count list, which has a fixed size of 26, contributes 1 space since it does not depend on the size of the input. The result list, on the other hand, grows with the number of characters in the input string, contributing n space in the worst case. Finally, since the input string itself is not modified, it does not add to the space complexity. Additionally, no extra data structures are used beyond the ones already discussed, so the auxiliary space is negligible. When we combine all these components, the total space complexity of this algorithm is n, which is dominated by the space required for the result list. To put this into context, let's compare it to a naive approach. A brute force solution might involve repeatedly finding the smallest or largest remaining character and appending it to the result, modifying the input string as you go. This would require scanning the string up to n times, resulting in a time complexity of n squared. In contrast, this optimized approach leverages character frequencies and the fixed alphabet size of 26 to achieve a much more efficient n time complexity. By avoiding unnecessary scanning and modifying of the input, the algorithm ensures optimal performance. When analyzing the algorithm further, the time complexity holds steady across different scenarios. In the best case, where the input contains only one unique character, the algorithm still processes all n characters for counting, building, and joining, resulting in n time. For an average case, with a typical mix of characters, the same operations are performed, yielding n time. Even in the worst case, where the input contains all 26 unique characters, the fixed alphabet size ensures that iterating over the characters within each pass of the loop remains constant work. Thus, the overall time complexity remains linear, or n. Mathematically, the while loop runs n iterations, and each iteration involves constant work due to the fixed 26-character for loops. As for space complexity, it is dominated by the result list, which scales linearly with the input size, leading to n space. In conclusion, this solution achieves an optimal balance between time and space efficiency, with n complexity for both metrics, making it a highly effective approach for this problem. When solving this problem, there are a few common mistakes that can trip you up. First, it's easy to overlook edge cases like empty strings, strings where all characters are identical, or those containing special characters. Ignoring these can lead to runtime errors or incorrect results, so it's crucial to handle them explicitly. Another common issue is inefficient iteration. For instance, if you repeatedly iterate through the entire string in a nested loop to find the smallest character, your solution ends up with a time complexity of n squared. This is far from optimal, especially for larger inputs. Additionally, many errors occur when comparing characters incorrectly. For example, failing to account for case sensitivity, like treating an AND as the same or relying on incorrect ASCII assumptions, can result in improper ordering or failure to meet the problem constraints. Finally, modifying the string mid-iteration is a frequent pitfall. Since strings are immutable in many languages, removing characters while iterating can lead to index errors or skipped characters, causing unintended behavior. Being mindful of these mistakes can help you build a more robust solution. Another critical aspect to consider is handling duplicates correctly. Assuming that all characters are unique or failing to maintain the correct count of each character can lead to inaccurate results. If duplicates are mishandled, the output won't meet the problem's requirements. Now, let's shift focus to some insights that can help you during interviews. Recognizing patterns is key. Many problems, including this one, involve repeatedly selecting the smallest or largest element. In such cases, a greedy approach or a priority queue is often far more efficient than brute force. Choosing the right data structures is equally important. For instance, heaps, hash maps, or frequency arrays are excellent tools for problems requiring frequent lookups or updates. It's also essential to clarify constraints with your interviewer, such as the size of the input, the types of characters allowed, and whether duplicates or special characters are expected. Lastly, always weigh the trade-offs between time and space. While brute force methods may have simpler implementation, they often come with higher time complexity. If memory usage isn't a limiting factor, you might prioritize a more efficient approach. This problem is closely related to several others that you might encounter on LeetCode. For example, LeetCode 3.16, which involves removing duplicate letters, or LeetCode 10.81, which focuses on finding the smallest subsequence of distinct characters, share some conceptual overlap. Similarly, problems like LeetCode 4.02, which is about removing k digits to form the smallest number, and LeetCode 31, which involves finding the next permutation, also challenge you to think about ordering in optimization. To tackle these problems, alternative approaches can be very effective. One such approach is the greedy method, where you use a stack to build the result string while maintaining lexicographical order. This method is highly efficient with a time complexity of O(n), but it does require additional space for the stack. Another option is the frequency count approach. Here, you use a frequency array or hash map to track character occurrences and then construct the result based on this data. This method is also time efficient but comes with the trade-off of needing extra memory for the frequency structure. Exploring these approaches can help you find the most suitable solution for different variations of the problem. Finally, let's consider the heap-based approach. In this method, a priority queue is used to repeatedly extract the smallest character. This approach is particularly efficient for scenarios involving dynamic input, where the set of characters might change during the process. The heap ensures that you can always access the smallest character in logarithmic time. However, the trade-off here lies in the overhead associated with maintaining the heap structure, which can make it slightly less efficient compared to a greedy solution in terms of constant factors. Nonetheless, this method shines when flexibility and dynamic updates are required, making it a powerful tool in your arsenal for solving problems like this one. Great job! Today, we explored the increasing-decreasing string problem and discussed an intuitive solution. Remember to practice string manipulation techniques and think critically about optimizing brute force approaches. Thanks for joining, and stay tuned for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!